Good morning, good morning. It's Anu again with another chemical engineering video, and today we're going further into thermodynamics and talking about PV diagrams and TS diagrams. And this will help build on some of the concepts we learned in the previous video, which was on more of a definitions video of what UH, S, and G is. So let's get into it. Now, I was mentioning the last video, right? In the last video, we talked about properties such as U, the internal energy, H, the enthalpy, S, the entropy, and G gives free energy. Now, if you haven't watched that video, I'll put a card up now. I highly suggest you watch those videos, but that video really was definitions. It doesn't really give us any tools to really work with, to really understand more advanced topics in thermodynamics, such as Carnot cycles and other thermodynamic cycles, which is what we're really building towards too with PV diagrams and TS diagrams here. So again, if you haven't watched that, I suggest you do that right now. But assuming you are familiar with those concepts, let's get into what PV diagrams and TS diagrams actually are. So a PV diagram, very unique name, is just simply a graph that charts pressure on the y-axis and volume on the x-axis. Now you may be wondering why do we care about P and V? Well, if you remember from our previous video, the definition of enthalpy, which is the internal energy plus PV. Why do we add the PV? Well, this PV is actually the flow work. So this is the work done by the fluid. And so more specifically, if we were to actually do this derivation here, dW is equal to the derivative of that product, P times V, which if we were to use the product rule, we get VdP plus PdV. And at constant pressure, dP is 0, so we get negative dW is equal to PdV, or work is equal to the negative integral of PdV. So the reason why we like these graphs is because we are working with integrals. So suppose I have a line like this. The area under this curve is the work. It's the work being done by this expansion or contraction, right? It just depends on which direction we're going. If I were to go from left to right, which is an expansion, I'm increasing the volume at constant pressure, then work is negative. And vice versa. If I have it going the opposite direction, a contraction, work is positive. And so PV diagrams are very useful because it allows us to graphically visualize the amount of work that's being done by the system. Okay, so that's PV diagrams in essence. So now let's take a look at TS diagrams. So like PV diagrams, we have T on the y-axis and S entropy on the x-axis. So whereas PV diagrams were all about work, TS diagrams are all about heat. If you remember the relationship we talked about in the last video, we defined the differential S as partial Q over T. Or in other words, partial Q equals TdS. Integrating that gives you Q equals integral TdS. And so now, if I have a line going like this, the area under the line, or area under the curve, is now Q. And depending on the direction, it's either heat in or heat out. So if I'm going increasing the entropy, that's heat in. And if I am decreasing the entropy, That is heat out. And so you might be wondering, why do we care about these diagrams in the first place? And the reason is because of cycles. Now, what is a cycle? I will just briefly introduce that concept here. So going back to our PV diagram, a cycle is quite simply just one in which you start at a specific point. Let's say you start at point A, and then you go around all the way back to A. So you go from A to B to C to D back to A. That is a thermodynamic cycle. You've gone around the circle here. And what's really neat about this is that if I were to take the area in this rectangle, let me do that with a different color here. If I were to look at the area in this rectangle, this is actually the net work. Because what I'm doing is I'm taking, in this case, we have two places where we have the volume constant and we're increasing or decreasing the pressure. So there's no work really being done there. So really the work net is the difference between this contraction and this expansion, the difference between that work there. And that's why the area here is work net. Similarly, if I were to do a similar completion of a cycle for the TS diagram, and I were to look at the area in here, this is Q net. So this is the net heat. So PV diagrams tell you about the net work for a cycle, and the TS diagram gives you the net heat, Q. Now, the most important thing to remember with thermodynamic cycles is conservation of energy. We are going from state A to state A. So we're going from A, and yes, we might have many different states. We have B, we're at C, we're at D, and so forth, right? But eventually we return to A. And so the question is, what is the change in the internal energy for one complete cycle? Well, it has to be zero. Energy can't be created or destroyed. U, H, S, and G, these are all stateful functions, meaning that they are specific to the state and not to the path, right? And I guess this is a good concept that I should have really introduced in the last video. So I'll briefly just mention it here. A stateful function is essentially one that depends on the state you're in, not the journey. So for example, if I have a mountain, I basically have two paths up the mountain. I can go straight up like this, or I can go in this kind of winding path up the mountain. So a stateful function might be the altitude. So regardless of the path that I take, getting to the top of the mountain is at the same height. A non-stateful function might be number of steps taken. This does depend on the path. If I take the straight path, it's going to be less steps than if I took the winding path. So the key to remember here is that U, H, S, and G, these are all stateful functions. They are dependent on a state. So if I go from A and it doesn't matter what journey I do, if I return to A, I must be back at the same internal energy state because energy cannot be created or destroyed. So delta U equals zero. And for a closed system, delta U will always equal Q net plus work net. So in other words, Q net equals negative work net. And now we can see the connection between the two diagrams, PV and TS. Those areas are going to be essentially equal. And we can see how exactly they are related to each other. So with that, let me actually introduce one of our first thermodynamic cycles here, the Carnot cycle. I won't go too much in depth on this one. I think it is helpful to maybe make a separate video about it, but I'm just going to briefly introduce this concept with the TS diagram here. So let's talk about the Carnot cycle. So the Carnot cycle, I mean, doesn't really matter where exactly we start, but we're going to actually start with we have a system, and then we put it in contact with a hot reservoir at TH. Heat is going to flow into the system, Q, and the system is going to expand. So work is going to leave the system. So on a TS diagram, we're at TH, hot temperature. We're at S1, and I am going to increase the entropy until I reach S2. So isothermally, I'm expanding at TH. Because I'm adding heat, I am increasing the entropy of the system. I'm moving the molecules in more configurations. So I have increased in disorder. So this is from A to B, A to B. And so on the PV diagram, I'll just do this here. The reason I wanted to start with the TS diagram is it's nice straight lines here. PV diagram is a little bit more complicated. Basically, the system is expanding, work is leaving the system. We are losing a little bit of pressure, but it is relatively parabolic. So this is A and B. Okay, so that's A to B. The next step is an isentropic expansion. Isentropic meaning same same entropy. The entropy is not changing. So what we're going to actually do is we're going to thermally isolate our system. So our system is now thermally isolated, Q equals 0, but we're still going to continue to expand. So work is continuing to leave the system. So we have work going out. And so what's going to happen is the temperature is actually going to drop. Drop to point C at TC, or cold temperature. And so entropy staying constant, we drop to TC. Again, this is for a reversible process. We're assuming that this entire process is reversible. So there is no entropy change, even though we've continued to expand. Okay. Then C to D. Now we place our system in a cold reservoir, TC, and Q is coming in, and we're going to do some work on the system. The surroundings are going to compress the system, so there is work being done on the system. Oh, wait, I forgot to do it on the PV diagram. This is isentropic expansion, B to C. So now we're going to increase isothermally, back to D. This looks sort of like this. And then lastly, going from D to A, we again isolate our system, Q equals 0, but now we're still putting in work. So this will increase temperature back up to TH, and that completes the cycle. So this is the famous Carnot cycle. And the key here to remember we talked about that relationship, Q net equals negative work net. So the net work that we get, right, the area of this rectangle, which is the net heat or negative net work, the key here to remember is that the net work is equal to, I'll do this in absolute values here, it's going to be equal to TH minus TC times S2 minus S1. Or in other words, what is the area of the rectangle, right? It's just going to be the height times the width. That's all it is. And so the question is, what is the actual efficiency of the system? And for that, it helps to understand what's the total heat that we're getting from the hot reservoir? What's the total input, heat input that we're putting into the system? Because the only real input that we're putting in is the heat, right? And so if we were to actually look at the heat, that's the area under this top line from going from A to B. And so the area of that rectangle, which we typically denote as QH, is equal to TH, which is the height, times S2 minus S1. Height times width again. Correct? And so the way we define efficiency here is equal to the net work that we get divided by the total heat input. So from the rectangle, we know that work net is equal to QH minus QC. Which means that the net efficiency is equal to 1 minus QC over QH. And by the way, I forgot to define QC. QC is the area under the rectangle on the bottom. So this is the heat rejected. So this is TC times S2 minus S1. So I noticed that S2 and S1 are the same. So 1 minus TC S2 minus S1 over TH S2 minus S1. These will cancel. So the efficiency of a Carnot cycle is equal to 1 minus TC over TH. So a perfectly efficient heat engine will either be operating at absolute zero, or the heat reservoir is infinite degrees Celsius. And we'll talk a little bit more about Carnot cycles and other thermodynamic cycles in a later video as well. So we'll dive into more details of this. But the key thing to remember here, if I were to do the TLDR, the short of it, PV diagrams show you the work, TS diagrams show you the heat. They're related to each other for thermodynamic cycles because in a thermodynamic cycle, we return to the same state that we started with. So the change in total energy is equal to 0. So that's where we can get this relationship, Q net equals negative work net. Anyways, that's it for this video. I hope this was helpful to you. And if you have any questions, leave them in the comments below. All right, I'll see you guys in the next one. Bye-bye.